Hello everyone, my name is Sebastian Moraga. Before we start, I want to thank the organizers for having us in this really nice conference, and I'm really looking forward to meet all of you next time in person. So before we start as well, I want to acknowledge that this is a joint work with Ben Adcock, Simone Brugiapaglia, and Nick Dexter. Ben is a professor at Fraser University, Simone is a professor at Concordia University, and Nick's a postdoc fellow at Fraser University. And myself, I'm a PhD student at Fraser. So the talk today is going to be about deep neural networks that are effective at learning high-dimensional Hilbert-Valued functions from limited data. So we're going to start with the motivation for this problem. The main motivation for us comes from parametric PDEs. Given some parameters, the PDE can take the form of an operator that's applied to some function with some boundary conditions. So we have the parametric variables, we have the physical variables, and this operator can depend on the parameters as well, but the differentiation with respect to the physical parameters. And given some y, this function is an element of the Banach or Hilbert-Valued space. For example, we have the simple diffuser equation with some boundary conditions and a diffusion coefficient. So why is this challenging? The main challenge is because this approximation can come from high dimension models. Often g is greater than 1 or could be infinite. This leads to something that we call the curse of dimensionality. Second, the space V can be an infinite dimensional space, could be a Hilbert-Valued space. So this leads us to a discretization, because we cannot work in V, so we have to work in VH, that is a discretization over the physical domain, which induces a discretization error. 3. The data could be corrupt. We don't know, we can have some modeling errors, numerical errors, random noise on the measurements. And of course, generating the data is expensive. Generating multiple solutions of the particular PDE using a black box model is expensive. Getting the data from MRI as well could be really expensive. So we don't expect to have an approximation to every function that comes from any model. We need to have some assumption on this function. The first one will be that f has an anamorphic extension from -1 to 1 to some Bernstein polyellipse. If we recall some classical results, the Bernstein polyellipse is just a region in the complex plane that has a foci in -1 to 1 and can be controlled by this rho. So classical results as well says if f has an anamorphic extension in this Bernstein polyellipse, we can expand this function in an infinite expansion. Many parametric DEs has this assumption, including elliptic diffusion equation, parametric IVPs, or if you want to know more, you can check these really nice papers. So what we want to do here is trying to do some deep learning approach instead the classical polynomial approximation. So what we're going to do now is give a deep learning approach to this, and in case you're not familiar with a deep neural network is or machine learning is, in a nutshell is just a concatenation of simple functions with some activation functions that you feed this algorithm with some parameters in this case, and you have an output, and you can tune the weights and biases such that you have a better approximation to what you want to approximate your function. So why using this approach? Because neural networks are capable of efficiently approximate function for a wide variety of classes. Smooth functions, piecewise smooth functions, HK functions. There's existing theorems about deep neural networks that approximate holomorphic functions. As well, these networks can achieve the same error as the best S-term polynomial approximation, and specifically, they can obtain errors proportional to exponential decay, where this depends on the region of holomorphic that I talked before. And the size and depth of these neural networks are bounded in terms of S and D. So now, how we feed this algorithm? How we construct this? So we want to obtain an algorithm that can be trained and can be tested on the sample points that we obtain. So given some parameters, each DI is uniquely represented at the evaluation of this F that lives on the discretization of this space, and we call this as the input of the algorithm. As an output, we want an expansion of an orthonormal basis, for example, an expansion of the physical domain as well, and we want this approximation f hat to approximate this function, and the values of this coefficient of this expansion are going to be the output of our algorithm. So the main results here, what we found is a practical neural network system theorem for Hilbert-Valued functions. Imagine that you have your f that has an homomorphic extension for some region with some sample complexity that is called this m tilde. We know that there exists a class of neural networks that come from a ReLU activation function, a loss function, a realized L2 loss function, are choices of these sample points such that any network that is trained from these points gives an approximation to f satisfying this bound error. What it does mean is we have three main errors here. The first one is approximation error that quantify how well f is approximated by the neural networks in terms of the sample complexity. The second one quantifies the errors in the points-wide evaluations of f as sample points. And the third one is because we are working in BH rather than B, so we have this discretization error that I talked before. I'm not going to give all the details of the proof, but what I'm going to do is just give the key insights of how we construct this. First of all, we consider orthonormal polynomials. We let U be the unit hypercube. We take some measurements from the uniform measure, and we use the tensor product coming from the orthonormal Legendre polynomial basis. So we let L2 rho be the Lebesgue-Bochner space of Hilbert-Valued functions that takes values on view and go to Hilbert-Valued function. And we consider polynomial approximation. For example, if f it lives in this space, then we can expand this function with these orthonormal polynomials, with these coefficients. And this coefficient could be a sequence in LP where we define this BP norm. That's going to be important later. So, in a nutshell, what we're going to do, the polynomial approximation we presented as a compressed sensing problem. So we let the lambda be a finite index set with cardinality n, and we define the normalized measurement matrix that takes into account the orthonormal expansion. And take attention to this because it's going to be really important later. We define the normalized measurement and error vectors, B and E, and the recovery of this polynomial coefficient, and at the end, the recovery of this function approximation is equivalent to solve this noisy linear system. So now we consider to recover this, the so-called squared Rho-Lasso problem, a minimization problem, to recover this coefficient. That if we obtain that, we obtain the approximation of our function. So where the neural network comes to play here. So the main result that we saw is that we can approximate these orthonormal bases with neural networks. We can use the result that emulates the polynomial approximation problem as a deep neural network training problem. So we can approximate, if we can approximate these polynomials, careful balancing the errors to this approximation, we have the main result. So now it's time to present some numerical results, right? So the main example we showed before what comes from a parametric PDE, right? So we want to present now the numerical results on a parametric PDE approximation. This example takes into account a physical domain that's going to take the unit square for our discretization. I'm going to take the parametric domain with uniform probability measure with the unit hypercube. Given some y in this domain, we seek a function that satisfies this differential equation. It's a diffusion equation with some diffusion coefficient and boundary conditions. So we want to compute, at the end of the day, is the approximation to this function with neural networks. And if you remember the two expansions, what we're going to do is expand this with a finite element basis, and we want to obtain the coefficient of this finite element approximation using neural networks. So given some y, we feed that in the neural network, and that gives us the approximation from the finite element basis. As a note, we don't implement exactly the same training strategy as the theorem, but what we're doing is emulating the orthonormal basis. So basically, it's really similar. Now, how are we gonna do the train and the testing? Because every time you have a neural network, you have to train and test the results. So given some data, some parameters, and the evaluation of these parameters that comes from a fixed finite element discretization, we want to minimize the loss function between the coefficients that give us the finite element solver and the coefficient that give us the neural network. So how we're gonna do this? We train this using two loss functions. The first one is gonna be the mean square, that is the really well known, and the second one is gonna be the energy norm, what we're gonna use to here. Because we want to see if taking into account physical part of the problem leads to better performance in the numerical results. And the testing, we compare the testing in the Lebesgue-Bochner space with the L2 norm in the physical domain and the H1 norm. And to do this, we use deterministic high order space grid stochastic collocation methods. Now, for the numerical results, we see that neural networks architected with the energy norm underperform identical architectures trained with the mean squared error. This is a little surprising because we expect that taking into account more information about the physical part of the problem will lead to better performance. What happened is that using the mean squared error was faster and better. And we see a big difference between the L2 norm for hyperbolic tangent, Rayleigh networks, and leaky ReLUs with 5 layers and 15 nodes per layer. So not everything is just comparing the errors. We want to show you a visualization comparative of what happened at the early train of the process and what happened at the end of the process. So what I'm showing here is a prediction of for u from a hyperbolic tangent with 5 hidden layers and 15 nodes per layers at this particular y. So at the start of the process, after just 2 epochs of ADAM optimizer with the mean squared error of 6.4, we have this visualization with a lot of spikes. It's not too bad in the sense that it was created just at the start of the process, but at the end of the training, after 2000 epochs of ADAM, we achieve an error of 10 to the minus 7, and you cannot see the difference between this one and the solution given by the finite element method. So in the next slide, we're going to compare the best state-of-the-art methods with our deep neural network approach. Using an elliptic PD with 30 dimensional log-affine parametric diffusion coefficients, and we see that neural networks cannot perform the best state-of-the-art polynomial compressed sensing methods. On the right-hand side, after 300 uniform random sample points, the hyperbolic tangent with 5 layers and 15 nodes per layer does really good compared to compressed sensing. And as well, rather than to just consider a diffusion equation, we want to see if we can use deep neural network to approximate a mixed formulation for a mixed boundary condition problem. So in this case, we're not only using the neural network to approximate u, but its gradient as well. And the result shows that deep neural networks can be used to approximate parametric PDEs with mixed boundary conditions using mixed formulations. This leads to approximate u and its gradient. But the result shows that errors for u are substantially smaller than those for these gradients. You can see that in the graph, that the errors for u are really much, like 10 times smaller than for this gradient. On the right hand side, you can see an approximation with the neural network of u and its gradient. As conclusion, we can see that neural networks are capable of approximating Hilbert-Valued functions from limited data. There exist neural networks architectures and training procedures that performs as well as best state-of-the-art schemes. Neural networks can be used to approximate mixed formulations, and using the mean squared error as a loss function leads to better and faster results than using energy norm, for example. And in practice, the neural networks can outperform or match best current state-of-the-art methods. So that was my presentation. Here you have some references, and if you have any questions, I guess you can send it to me. Thank you.